Network monitoring and traffic analysis are about turning the network from a black box into something you can reason about, because traffic is the most honest story your environment tells. Hosts can lie in logs, applications can fail to record events, and attackers can tamper with local evidence. But packets still have to move if anything meaningful is happening. When you can observe what moves across the network, you can infer relationships between systems, detect unexpected behaviors, and validate whether controls are actually shaping traffic the way you believe they are. This matters for prevention, detection, and response because it provides ground truth about communications, not just intent or configuration. The end goal is not to stare at dashboards, but to understand what normal looks like, notice what deviates, and be able to explain and trace those deviations with confidence. Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. The sources you use for monitoring determine what questions you can answer, and the main categories are flow records, packet capture, and device telemetry streams. Flow records summarize conversations, typically describing who talked to whom, over which ports, and how much data moved, without storing the full contents. Packet capture collects the actual packets, which can include payload and protocol detail depending on where you capture and how you store it. Device telemetry streams include router and switch counters, firewall events, intrusion detection alerts, wireless associations, and other signals emitted by infrastructure and security devices. Each source has a different cost, a different privacy impact, and a different investigative value, so you choose them based on what you need to see and what you can sustain operationally. A strong program uses multiple sources because no single view answers every question you will face. Flow data is often the first layer because it scales well and gives you a structured picture of conversations by endpoints, ports, and byte counts. When you look at flow, you are not looking at individual packets, but at aggregated summaries that describe a session or a unidirectional stream over a time window. That summary can tell you that a workstation spoke to an external address over a particular port and transferred a surprising amount of data, or that a server suddenly began initiating outbound connections it never made before. Flow is especially useful for answering who and how much questions quickly, and it supports detection analytics that rely on trends and patterns rather than deep content inspection. The limitation is that flow usually cannot tell you what was in the traffic, so it is strongest when paired with other context, such as domain name data, identity, and asset role. Packet capture exists for the moments when payload-level detail is required, because sometimes you need to see protocol fields, handshake behavior, or even content to understand what actually happened. Packet capture can validate whether a connection was truly an interactive session or merely scanning noise, and it can reveal application layer behaviors that flow cannot describe. It is also essential for troubleshooting complex issues, because timing, retransmissions, and protocol negotiation details often explain failures that higher-level logs hide. The cost is that packet capture is storage-intensive, sensitive from a privacy standpoint, and difficult to manage at scale without clear scoping. This is why many organizations use selective capture strategies, capturing at key choke points, applying filters, or retaining short rolling windows that can be pulled when an incident occurs. When you deploy packet capture, you are making a deliberate decision to hold high-value evidence, and that decision needs governance to match its power. Baselines are what make monitoring useful, because without a sense of typical patterns, you cannot reliably separate real anomalies from ordinary variation. A good baseline describes behavior by time, segment, and application because a user wireless network has a very different normal than a data center segment, and daytime behavior differs from overnight batch processing. Baselines also include the rhythm of your environment, such as patch windows, backups, and scheduled data transfers, which can otherwise look like suspicious spikes. The point of baselining is not to freeze behavior into a single expected shape, but to understand the range of expected activity and the factors that drive it. When you know what normal looks like, you can ask better questions, tune detections, and avoid chasing noise that burns analyst time. Anomalies are the deviations that matter, and common examples include unusual destinations, unexpected data spikes, and rare protocol usage. Unusual destinations might mean a device is reaching out to infrastructure it has never contacted, or it might mean a legitimate new service was deployed. So your job is to assess whether the destination makes sense for that asset and role. Data spikes can indicate exfiltration, staging, backups, or misconfigurations that cause loops and retransmits, so you need context and sometimes packet-level validation. Rare protocol usage can be a strong signal because attackers often rely on uncommon ports and protocols to avoid simplistic controls. But you also see rare protocols during legitimate troubleshooting and specialty operations. The right approach is to treat anomalies as hypotheses, then test them using additional signals rather than assuming every deviation is malicious. That testing mindset is what turns monitoring into disciplined analysis instead of reactive guessing. Encryption changes the analysis problem because it reduces content visibility and pushes you toward metadata and endpoint context, which is not a loss so much as a shift in emphasis. When traffic is encrypted, you may not see payload content, but you still see who is talking, how often, for how long, and how much data moves in each direction. You can also observe handshake behaviors, certificate details when available, and patterns such as repeated short sessions or long-lived connections that do not match an asset's expected role. Endpoint context becomes more important because you need to know whether the initiating system should be making outbound connections at all, and whether the destination aligns with business function. This is why asset inventory, identity correlation, and network segmentation are not separate from monitoring. They are the context that makes encrypted traffic analysis actionable. In practice, many detections in modern networks rely on metadata patterns precisely because encryption is the norm. Domain name system telemetry is a particularly valuable lens because it sits at the intersection of human-readable intent and machine-level connection behavior. Many command channels and malicious workflows rely on domain names even when the subsequent traffic is encrypted because the attacker needs a way to locate infrastructure and rotate endpoints. By watching domain name system requests and responses, you can identify suspicious domain usage patterns such as newly registered domains, high entropy names, unusual query volumes, or repeated failed lookups from a single host. Domain name system data also helps interpret flow records because an external address may be hard to classify, while a domain name can reveal whether a connection is likely to be legitimate software updates or something that does not belong. You do have to handle domain name system data carefully because it can be sensitive from a privacy standpoint and because modern technologies can change where resolution happens. Even so, domain name system remains one of the most actionable telemetry sources for understanding where systems are trying to go. Time accuracy is a surprisingly foundational requirement because monitoring is ultimately a correlation problem, and correlation fails when clocks drift. If one sensor timestamps an event a few minutes ahead and another timestamps it a few minutes behind, you can lose the ability to confidently connect a domain name system lookup to a subsequent connection, or a firewall event to an authentication event. Accurate network time supports incident reconstruction, where you sequence events and infer causality, and it also supports automated analytics that assume timestamps are reliable. This is especially important when you combine signals from packet capture, flow, endpoint telemetry, and identity logs, because each system has its own buffering and reporting characteristics. The practical goal is to treat time as shared infrastructure, ensuring that critical systems and sensors maintain consistent time sources, and that drift is detected and corrected. Without that, you can end up with evidence that is technically correct but narratively unusable. Sensor placement determines what you can see, and it is useful to think in terms of north-south traffic and east-west traffic. North-south refers to traffic entering and leaving an environment, such as internet egress and ingress, where choke points make monitoring efficient. East-west refers to traffic moving laterally within the environment, such as server-to-server communications and workload interactions, which is where many attacks unfold after an initial foothold. If you only monitor north-south, you may miss lateral movement and internal staging, and if you only monitor east-west in a limited segment, you may miss the external command and control that directs those actions. Placement also affects whether telemetry includes internal context, such as seeing traffic before it is translated, proxied, or encrypted again by intermediate devices. Good placement is a design decision, not an accident, because it defines your visibility boundaries just like segmentation defines your access boundaries. Filtering is how you keep monitoring sustainable, because raw telemetry can drown you in volume and hide meaningful signals under benign noise. Filtering can mean focusing on critical segments, such as identity services, administrative networks, and sensitive data zones, where deviations have higher consequence. It can also mean focusing on key services and protocol types that are commonly abused, or excluding known noisy traffic patterns that have been validated as normal. The goal is to preserve coverage where it matters while reducing collection and analysis costs, because a monitoring system that captures everything but cannot be searched or analyzed in time is functionally ineffective. Filtering is also a quality control mechanism because it forces you to articulate what you care about and why, which improves detection design. When filtering is done thoughtfully, you reduce false positives, improve analyst efficiency, and make retention decisions easier. Retention decisions balance forensic value against storage and privacy constraints, and that balance is unavoidable because traffic evidence can be both large and sensitive. Longer retention provides more opportunity to reconstruct incidents, identify dwell time, and validate whether suspicious behavior started weeks ago or yesterday. It also increases storage costs and increases the exposure of sensitive metadata and potentially sensitive content, depending on what you retain. Different telemetry types often get different retention windows because flow summaries are cheaper to keep long-term than full packet capture, and high-sensitivity logs may require tighter access controls and shorter retention. Retention should align with the organization's risk posture, legal obligations, and incident response maturity, because evidence you cannot access in time or cannot store responsibly is not helpful. A mature program treats retention as a policy decision backed by architecture rather than a default setting that accumulates by inertia. Correlation is what turns network signals into security understanding, because traffic alone is ambiguous until you connect it to identity, asset roles, and vulnerability context. When you correlate a connection with a user identity, you can distinguish automated service behavior from human-driven activity and detect unusual access patterns. When you correlate with asset inventory, you can identify whether a device is a database server, a workstation, or an unmanaged endpoint, which changes the interpretation of its traffic. When you correlate with vulnerability information, you can prioritize anomalies that involve systems known to be exposed to particular exploit paths, making triage more risk-based. Correlation also improves traceability because it allows you to explain not just that traffic occurred, but why it matters and what it implies about control effectiveness. This is how monitoring becomes actionable, not by collecting more, but by linking what you collect to the context that makes it meaningful. The payoff is that monitoring converts raw traffic into actionable understanding and traceability, which is exactly what you need when security shifts from theory to investigation. Flow records give scalable summaries, packet capture provides deep visibility when the situation demands it, and device telemetry adds infrastructure perspective that fills gaps in the story. Baselines and anomaly detection let you focus attention where behavior deviates from expected patterns, while encryption pushes you to leverage metadata, identity, and endpoint context more intelligently. Domain name system telemetry and accurate timekeeping strengthen your ability to correlate events across systems, and thoughtful sensor placement ensures you see both external movement and internal lateral behavior. Filtering and retention keep the program sustainable and defensible, balancing operational cost and privacy concerns against forensic value. When these elements work together, the network stops being just a transport and becomes an evidence source you can trust. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.